14. Okay, so go back to lecture 14 and refresh your memory on theorem 46, first part, okay, which says that if you have two cosets that are equal, right, they have equal members, so if they're the same coset, this is true if and only if this member x inverse y belongs to the, well, whatever this is. In this context, it's the kernel. Right? Before, you're probably familiar with xh equals yh. So x inverse y belongs to h. Now h was just your normal subgroup, right? But k is a normal subgroup. So I'm just, instead of h, I'm just putting k here, right? So if these two subgroups are equal, therefore, if you go that way, x inverse y belongs to your kernel. Okay? So now we do have this xk equals yk. That would sort of be your x, and that'd be your y, right? Now the binary operator here is plus, so you got a plus here and here, which is that equals that. All right. So if that's your x and that's your y, what is x inverse? Well, it'll be just, you put a minus here, right? Remember that residue classes behave very much like integers, right? You can add them, you can multiply them, and stuff like that. All right. Now we forget about the k's; they sort of cancel. So now you got it. So x inverse y will be like this, right? So minus I and minus j, minus I minus j. That's your x inverse, and your y is your KL. Now, so now you've now got these minuses, and just from the simple laws of arithmetic of residue classes, well, you got stuff like this. Go back to way back when we're talking about residue classes. So this is why residue. I have again it's shorthand. Strictly speaking, I should have a modulus, some mod n here. So residue classes behave like integers. There's a kind of integer arithmetic, not fully addition, subtraction, multiplication. I don't think there's any division. Right? Okay, so x inverse y takes this form. Right? So because x inverse, you'll have a minus here and a minus here, and the k's go away. On both sides. Forget about them. So take this over, and then you'll have the form of a plus b, but well, in this case it'll be minus a. All right, and so you can rewrite it this way, minus a plus b, which is what you've got here. Right? Now going the other way, from here back to here, you can rewrite that in this form. Okay, and that whole thing from theorem 46 part 1, that whole thing belongs to the kernel. So all this belongs to the kernel. Okay. Now I, j, k, and l can only be 0 or 1. They're the only two possibilities, 0 or 1. Now the only way you can have this belong to k and I, j, k, and l only take that is 0 or 1. The only way you can have those two, this and this together compatible, the only way that can be satisfied, if you go through all the little details, is if I equals k and j equals l. Now I haven't proved that. It's a bit tedious. do that at home if you really want the details. Okay. So, so summarising, the only way that and that are compatible is if I equals k and j equals l. In other words, you've got a contradiction because here we said they were different. Right? We took two different ones and said they were the same. And now if they are the same, then I equals k and j equals l, rather than I being different from k and j being different from l. Okay? So we have a contradiction, and therefore instead of these two here being different, they must be the same. Okay, so therefore these four cosets are distinct. They're different, right? Okay. Now, so we've now got the quotient group. We've got the four cosets that are the members of the quotient group. Now, so in other words, the quotient group is of order 4. Right? It's of order 4. Now, we have done in an earlier lecture. We looked at, proved every possible non-isomorphic group of a given order, given size, and we went up to order 11. Right? So for all those orders, 11, 10, 9, 8, 3, 2, 1, we know for each order how many and what the groups are that some candidate group of a given order, which ones it could be isomorphic to. For example, a group of order 4. There are only two possibilities. There are only two non-isomorphic groups of order 4. Now, there's always the cyclic group, right? Of any order, you will always have the cyclic group of that order. So that's one candidate, and that's true of any order. And the other one we proved, if you're forgetting, go back to what chapter was that? With 19, you forget; they tend to merge. Groups to order 8, wasn't it? What chapter number was that? (15). So go to lecture 15 and look up those proofs. Right? So groups to orders up to 8. Now for order 4, groups of order 4, one possibility is that group is the cyclic group, and the other is that it's the product group of C2 times C2. And what's C2? That's the cyclic group of order 2. Okay, so the product group of C2 times Bx C2. Right? So our quotient group with these 4 cosets, they're the members of the quotient group. What type of group is that? Is this quotient group that we've found? Is it isomorphic to? Well, there are only two possibilities, right? It's either isomorphic to the cyclic group C4, or it's isomorphic to the product group C2 times C2. There are only two possibilities, because there are only two non-isomorphic groups of order 4. Right? So which is it? Is this isomorphic to C4, or is it isomorphic to C2 times C2? Well, if it's isomorphic to the cyclic group C4, that means that the order of the elements 1, 2, 3, 4. If that group, that quotient group, if it's cyclic, then that group must have a generator, right? So typically, once you've found a quotient group and you're trying to see which group that it's isomorphic to, typically you will find the order of the elements of your quotient group and have a look to see if any of them is a generator of the quotient group. Now, in this case, except for the unit always has a. Now, the unit's an element, right? And the order of the unit element is 1, but if you actually calculate the order of the other 3 elements, like group, always that damn confusion. Okay, the orders of the other 3 elements, not 4, they're all 2. Okay, therefore, none of these is a generator of the group. Right? There is no group generator, and therefore this group here is not cyclic, right? Because there's no generator, there's no group generator, so it's not cyclic. Now, since there's only 2 possibilities, right? It's either isomorphic to C4 or it's isomorphic to the product group C2 times C2. Well, it's not isomorphic to C4 because if it were, there'd be a generator, but there's no generator. Therefore, it's not a cyclic group C4. Therefore, it must be isomorphic to the other one, right? The product group C2 times C2. So the quotient group here, here are your 4 cosets. That quotient group is isomorphic to Z2 times C2, the product group. Okay? And we'll run out of board. Next session, still on theory, we will get to one of the big theorems. In fact, it's the the title of the whole lecture, the first isomorphism theorem. Now, notice the isomorphism. So we're talking about not a homomorphism. We're in the context of homomorphism, but we will derive something that's isomorphic. And be careful, be warned. Textbook says the same thing. The slightly more advanced textbooks, say Masters 1, M1 level, there are usually 3 isomorphism theorems. And what some authors call the first are not the first for other authors. So there's no real consensus yet. There's still a bit of confusion about that. So be prepared to be confused as you go from one text to another. Okay? Well, I'll show next session. What is called the first isomorphism theorem isn't necessarily what some other author, not Barnard, some other author calls the first isomorphism theorem. But it's one of the great results of group theory, so a major result, and the topic of the next session. So stop there.